Hello students, welcome back. Let us resume our discussion in section 1. Previously, we defined trigonometric ratios of arbitrary angles. We begin with a circle centered at the origin with radius r, and we can inscribe any angle here. And then we can inscribe a triangle, a right triangle based upon the terminal point of this angle. How do I do that? Angle in question is always at the origin, and we can inscribe a right triangle whose right angle at the x-axis like this. And this right triangle, and consequently this acute angle here where my mouse is running around, this angle and the starting angle are of course related. In this particular case, they differ by pi, 180 degrees. Let's run it again. Oh, this is too close to 90 degrees. Okay, in this case, the angle in question, and then inscribed right triangle is here, and acute angle is over here. So this acute angle plus this angle in question add up to pi, 180 degrees. So this acute angle is actually a supplementary angle. 180 minus the angle in question, or pi minus that angle. How about fourth quadrant? Yeah, okay, in this case, angle in question goes all the way up here, and then plus this acute angle will add up to 2 pi. So this angle is actually 2 pi minus this acute angle. So this acute angle and right angle trigonometry and the arbitrary angle that we are going to study are intimately related like this. Plus pi, or pi minus of that, or 2 pi minus of that, kind of like that. And no matter where your terminal angle is in this particular case, this terminal point is in the fourth quadrant. Previously, they used to be in, well, all over the place. Second quadrant, fourth quadrant, third quadrant, fourth quadrant, whatever. No matter where the terminal point is, the trig ratios are defined exactly the same way. Sine is y over r, vertical over radius, cosine is x over r, horizontal over radius, tangent is y over x, vertical over horizontal, and cosecant, secant, and cotangent are their reciprocals. Therefore, cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent, etc. Therefore, we have this reciprocal identities immediately from the definition. Okay, all right, that was a quick review. And then we went through the signs as well, right? A smart trig class. First quadrant, all positive. Second quadrant, sine is positive, the other two are negative. Third quadrant, tangent is positive, but the other two, sine and cosine, are negative. Fourth quadrant, cosine is positive, but the others, sine and tangent, are negative. A smart trig class. We can use that kind of arguments to answer these kind of problems. Say, for example, cosine is 5/7, positive, and tangent is negative. What quadrant is it in? It must be quadrant number 4. How about this? Cosecant is 9/4, so sine is 4/9, is positive, and secant is negative, therefore cosine is negative. Sine is positive, cosine is negative. What quadrant is it? Must be quadrant number 2. So quadrant 4, quadrant 2, and then you can draw appropriate triangle in appropriate quadrant like this. Quadrant 4, and hypotenuse is 4, and then horizontal is 5. Let's find out the vertical. And then actually I'm missing negatives here. But if you don't care about pluses and minuses, just the size of it, then you don't really need negative. And then you can figure out pluses and minuses later using a smart trick class. In any case, we have x, y, and r values, so sine, cosine, and tangent, they're all there, and they're reciprocals too. Same for the second problem. Determine quadrant. Draw the picture, and then determine horizontal x. Again, I'm missing... Oh, okay, some further typos. Okay, alright, it's all there now, all corrected. So we have all those x, y, and r values. And therefore, we have all the trig ratios accordingly. Yeah, I usually write multiple of those problems in both first exam and second exam with various variations. So please prepare all those. And you have to justify all these graphically. So please prepare to draw the pictures accurately. I'm checking if all the pictures are indeed correct, and yes, they turn out okay. Alright. And then what's next? Basic angles, alright. Here's a summary, unicircle diagram. X, y are cosine, sine. X, r is cosine, y, r is sine, but this is unicircle, radius is 1, so no denominator. X coordinate just cosine. Cosine of 60 degrees, for instance, is 1/2. X coordinate is cosine, so cosine of 4 pi over 3, for instance, is negative 1/2. And then if you're interested in tangent, y over x. So like this one here, 1/2 over negative square root of 3 over 2. So negative 1 over square root of 3 is tangent of 5 pi over 6, and so on and so forth. You can answer all those here. Or you can inscribe basic triangles. Yeah, triangle number 1 on the left, triangle number 2 on the right. And then in the first quadrant, that's a summary. In 0 and pi over 2, we have degenerate triangles. So line segment horizontally and vertically. And the others are basic triangle. Triangle number 1 for pi over 6 and pi over 3. And for pi over 4, triangle number 2. That's why number 1 is a little bit more important than number 2. Quadrant 2, how about that? Here's a summary. And again, we are doing something similar. Degenerate triangle, a line segment. Horizontal line segment, another degenerate triangle. And then 2 pi over 3, triangle number 1, inscribed like this in the second quadrant. Triangle number 1 again, inscribed this way on the second quadrant. And then triangle number 2, 45 degrees. That's a summary. We can do the same thing in the third quadrant. That's a summary. And then you can inscribe triangles. Degenerate triangle, horizontal line segment. Another degenerate triangle, vertical line segment. Otherwise, triangle number 1 in the third quadrant. Another triangle number 1 for third quadrant. And triangle number 2, like that. So that's going to give you all the basic angles for third quadrant. Do the same thing for fourth quadrant. Here's a summary. And then degenerate triangle, line segment, vertical, horizontal line segment. And then as for the others, well, the same as before. Triangle number 1 in the 4th quadrant like this, and like that. And then triangle number 2 in the 4th quadrant. In the end, the summary is right here, the unicircle diagram. Please remember this. And I posted this unicircle diagram on the announcement page. You can print out and use it for the rest of the semester. Alright, so basic angles done. A little bit more problems here. How about some area problems? Remember the area formula for the sector? Well, area formula for the arc, S is r theta. That's because theta was defined that way, S over r. As for the area, how do we get that? Well, from entire area pi r squared, we just have a piece of pi. So theta radian out of total 2 pi radian, multiply that and simplify. That's how you get this formula for radian measure. For degree measure, we have to multiply degree angle out of total 360 degrees. Same for the circumference and same for the area. Why didn't I put similar formula here for... Oh, okay, all right. Yeah, okay, all right. I have circumference formula here, okay, for degree angle, and okay, all right. So that was for sector. Okay, all right, that was for sector. Now, another formula here, that's for triangle. Area is 1/2 AH, 1/2 base length times height. And this is something we have been using for a long time that goes way back to elementary school days. The next formula here is new, 1/2 AB sine of theta, when we have 2 sides and an angle in between. We can deduce one formula from the other like this. So here's an acute triangle, and everybody can see that the area is 1/2 A times H. Yeah, this one. Base length times height divided by 2. But from this right angle trigonometry and this green right triangle, sine of theta is H over B, vertical over hypotenuse. Flip this denominator B over to the other side, we have H is B times sine of theta. So replacing B sine of theta in place of H here and simplify, yes, that's how we get the second formula. So the area formula for triangle, when we have 2 sides and an angle in between, SAS. In that case, yes, here's a formula, 1/2 AB sine of theta. Interestingly, it works for obtuse triangle too. Let's see. H is same, B sine of theta, or rather sine of theta is H over B. Look at this as the origin here. Angle in question is the origin, and we have a circle going around there with radius B. And then look at this green triangle. You can inscribe a right triangle like this, and this angle here is a supplemental angle, pi minus theta. Sine of pi minus theta, vertical over radius. H over B is the same. Sine of theta and sine of pi minus theta is the same. So H is B sine of theta, and put it in, and then we have the same formula, 1/2 AB sine of theta. So what do you get? We get the area formulas for sectors and triangles. Remember these, and in the next video we'll come back and do some example problem with the areas.